the situation in this problem is that you have an aluminum wire with a cross-sectional area of 4 times 10 to the negative 6 meters squared. Just notice that area should be squared. And what we're asking is, what is the drift velocity? Drift velocity is talking about an electron that, in a wire that feels the potential, and then they are drifting as a result. So think of electrons as like a river, and this water current, and then you have little water molecules drifting along. It's the same idea. It's just like a whole bunch of electrons, like in a sea of electrons, and then electrons are drifting along. And the question is, how fast are they drifting, given that we have this current of 5 amps? Right? So the current, overall current is 5 amps, and we're asking what the drift velocity of the electron is. We know that the density of aluminum is what we look up, so look that up in your textbook or online, and it's going to be 2.7 grams per centimeter cubed. And we want to make use of this equation. That's the equation we want to use. This is what you should write down on your equation sheet for your test this Friday. Current equals NQA V drift. And what are each of the parts? Well, N is going to be the atoms per meter cubed. So the atoms per volume. That's what N represents. M represents the grams per atom. M represents the grams per atom. Because then we can find the N, little n, atoms per volume, which will be the density of aluminum divided by the mass per atom. So, I guess another name for that is the molar mass. Is that correct? The molar mass. The amount of grams. Well, actually, no, that's not moles. Someone else got to check me on that. But anyways, the point is that you get the M and you get the N, and then you get this number here, that little n, because you want to plug that in. And you also already know the charge, right? It's 1.602 times 10 to the negative 19 coulombs. And we were given the cross-sectional area, right? So we just do a little bit of algebra. We find V drift equals the current divided by NQA. And right, you just plug it in. And that's it. That's the first problem. The takeaway is that you got to know how to manipulate your units. That's the whole takeaway. It's like in chemistry. You have to know, look at what the units are, and look at how I can multiply or divide to get the units that you desire. That's the takeaway. And that's because practice this. You need, even though it's real simple, practice it, because on a test it's like, oh no, I can't get the right units. So you want to be able to know how to do that really quickly, so then you're not fumbling with that on the test. All right, so that's basically it. Just step 1, step 2, step 3, and then plug it in step 4. Questions? All right, guys, here's the next problem about another wire, but this time it's a mystery wire. Before we were talking about aluminum, this time we have some mystery wire. And these are the parameters that they give us. That it's a very long wire. It has a diameter of 2 millimeters. The voltage that's running through this wire is 9.11, and the current running through it is 36 amps. And we're going to assume that the temperature is at room temperature, 20 degrees. It doesn't really matter in this problem, but in the next problem we'll talk about how the resistance of a wire varies with temperature. For this one, since it's 20 degrees, we can safely use this one. I think this one's valid for the room temperature one. So with this one, capital R is resistance of a wire. Not radius or anything. Resistance of a wire. It's going to be equal to the density of whatever that wire is made out of, divided by the area, times by the length of that wire. So this is another equation to put on your sheet. And if we're given the diameter, we know that the circumference of a circle, the area of a circle is pi r squared. But we can also write pi d squared over 4. That's also the same thing. So we can write that one. What you want to do basically is solve for the density, because it's the only thing that's missing in your equation. See? It's the only thing that's missing. Well, actually, there's 2 things that are missing. The density and the resistance. However, you know that the resistance is equal to the voltage divided by the current, because of Ohm's law. So we can plug this step in, step 2, plugging in the resistance into this equation after solving for the density. And then we carry it on through, plug it in, and we get that this value for the density ends up being the material of silver. So if that question was that on the test, it would be something like, what is this mystery wire? And then there's going to be a table of values. Or sorry, no, it's going to be A, gold, B, copper, and then C, silver. And then each of A, B, C, D, all the choices are going to be different densities. So then you know that you're solving for density. And then whatever it is, it's like, oh, okay, it must be silver, because it's that density. Because each material has its own density. So that's the second problem. This one is talking about the central equation to write down in your equation sheet is this one. The final resistance of a wire that depends on temperature is given by this. It's the original resistance at some initial temperature times by 1 plus alpha. Alpha is specific to the material. In this case, we're talking about tungsten, so we can look that up as well. The alpha value for tungsten is 4.5 times 10 to the minus third per degree. That's the alpha value. Change in T, that's change in temperature. That's what it's saying. So change in temperature, we know that's T final minus T initial. So basically, the question is asking, well, if these resistance values that we measure from the start, that, oh, it's 19 ohms at 20 degrees C. But then when we increase the temperature, when we measure it again a second time, we find that the resistance is 140 ohms. What is that temperature that we increased it to? What is that temperature? So we're going to use this equation here. This assumes that resistance varies linearly with temperature. So that's why this is a linear equation, you see here. So basically, rearrange, right? Get delta T. Get change in temperature. Once you get the change in temperature, you're just going to plug in what you have. You're going to get that amount. But don't forget the last step, right? Because that's just delta T. Delta T is T final minus T initial. So you have to add T initial to the other side, right? Add that 20 degrees, and you'll get 1440 degrees Celsius. So that's really hot. It's 1,440 degrees Celsius. It's super hot. So you don't want to touch that light bulb when it's really hot. So that's basically it. It's really simple, right, guys? Any questions on that? This one's talking about a nichrome wire, all right? And we have 3 questions to ask. What is the electric field inside a wire if this wire is attached to some voltage source? What is the power delivered to it at 20 degrees Celsius? And what is the power delivered to it at 304 degrees Celsius? So that's like really hot. Maybe it's like on fire. I don't know what fire is. But looking at the first one, what is the magnitude of the electric field? Well, we get that in 3 steps. We're going to first use the equation, resistance equals resistivity. This is not density. This is not mass density. I made that mistake before in explaining this equation. This is resistivity times length divided by the cross-sectional area of the wire. So you have the resistivity value is specific for the material. So for nichrome, it's 1.5 times 10 to the minus 6 ohm meters. And we plug in the other parameters, we get that the resistance is 298 ohms, and that's true when it is at 20 degrees Celsius. We use Ohm's law, V equals IR, and we know that the current was 0.5, because that was given to us, times the resistance that we got. So this is how much voltage is applied to the wire. And lastly, going back to our equations about electric field, remember electric field is voltage per meter. Right? You guys remember that. Voltage per meter. So you can see that electric field, this makes sense that this is voltage per length. Voltage per length of that wire. So we can take 149 volts divided by the length of the entire wire, 25 meters, that was given, and we get this value, 5.97 volts per meter. That's the electric field value inside the wire. We move on to part B. It's only one step, because now once you, well actually these are already given. Oh actually no, once you figured out 149 was the voltage, and you were given the current, and then you get that this is the power delivered. This is how many joules, joules per second that is delivered to your wire. That's at 20 degrees. Now, part C is that if I increase the temperature to 304 degrees Celsius, really hot, how will the power change if you kept the voltage constant? And so then we're going to use this equation, the equation about how resistance changes as a function of temperature linearly. Right? So we take the value, the original one is 298. The change in temperature, well, this is 340 minus 20 degrees, that's 320, right? That's going to be that. Alpha value, that's going to be specific to nichrome wire. So that's going to be 0.4 times 10 to the minus 3 per degree. And we get this new resistance. So at that higher temperature, the resistance has changed to 337 ohms. Which means the current has changed. Because the current now is going to be divided by that new resistance. Current is voltage over resistance. It's the new resistance. So it's 149 because we're holding voltage constant by the new resistance. And then we get this, the new current that's running through it. Because we have a new current, that means we have a new power. We have a new value for the power, which is going to be 66.1 watts. What's the takeaway? Well, now that you guys know how to use these equations, you see that the conceptual question may be, if we increase the temperature, what happens to the power? The power decreases. We increase the temperature, the resistance. What happens to resistance? The resistance goes up, right? Because it was 298 when it was at 20 degrees Celsius, and then when we increase it to 340 degrees Celsius, it's now 337 ohms. So resistance goes up. So let's see. Maybe we can talk about how, what happens if the cross-sectional area is larger? So if you have a thicker wire, what happens to the resistance? A is very large. Yeah. So then the resistance lowers. It lowers. Yeah. Because this is very large, and the resistance will be a smaller value. Yes. So now, if it's a thicker wire, what happens to the power? So what happens to the power? Anyone can take a guess? If you have a thicker wire, resistance is smaller. If resistance is smaller, then current is higher. And if current's higher, then power's higher. Right? Cool? You see that? That's the kind of thinking you want to get when you have those kind of concept questions. So multiple choice ones that actually kind of things like that. That doesn't require calculation. Okay, we have a circuit here with two capacitors. One that has a capacitance of 1 and the other one of 3. So this one holds 3 times as much charge as that one. The situation is that at t equals 0, there's no charge on that one. But we place 1 charge there when the switch is not closed. When the switch is closed, that's why I say that t greater than the initial time, the circuit is allowed to reach equilibrium. So there's a charge here, some amount of charge, I don't know what it is, some charge. And when we put it there, they're going to redistribute themselves. Right? And we're asking questions of what's going to happen, what's the voltage across each capacitor when they've finished redistributing themselves. So what is the final voltage, that's what it's saying, at equilibrium? Well, we know in general that charge equals capacitance times voltage, right? Or we could say voltage equal to charge divided by capacitance. But in this case, because we're talking about the whole circuit, we want to find the equivalent capacitance. And we see that this circuit is in parallel. The capacitors are in parallel. So we add them. So just 1 plus 3 is 4. And then when we answer that question, since we don't know the value of Q, we leave it in terms of Q. And in terms of, Q over 4C, right? So that's how much voltage is on across each capacitor. And then the second question is how much charge now is on each capacitor. And actually it doesn't come to a surprise. Take a look at this. When we do charge equals capacitance times voltage, right? We plug that voltage, that's true for both, that's what's going to happen. And when we multiply them out, you see that it's 1/4 Q and 3/4 Q. That makes sense. Right? Because look, it was 3 times as much charge as that one, so it holds 3/4 of the total charge, and this holds 1/4 of the total charge. Makes sense, 3-to-1 ratio. Cool, right? So that all makes sense. And actually, let me back up just before I talk about part C. As I've indicated here, 1. Before we started, you know how we put 1 charge on this first capacitor here? So we know that the energy of a capacitor is 1/2 CV squared, and then just simple manipulation, you see that since we have 1, so so this would be 1, and then 1 charge, 1 Q over that capacitance, right? So that's why this total energy from the beginning is this, Q squared over 2C. That's the original energy on the circuit. So energy is conserved, so keep that in mind. We're going to do that in part D. But now, okay, let's go back to part C now. Part C, we'll use the same equation, right? But it's going to be specific to each capacitor. So look, this one for the smaller one, for the bigger one, for the smaller one, look, this is 1 capacitance, so it's 1/2 C, and then the voltage we got before, Q squared, Q over 4C, that quantity squared because it's V squared, right? For the bigger one, it's 1/2 3C. See, emphasize this. Because we're talking about the capacitor of the bigger one, so it's 3C, and then Q over 4C squared. And so these are the energies for each of the capacitors. And again, you see that the ratio is 3 to 1. So it holds 3 times as much energy. That makes sense. It holds 3 as much energy as the first one. Now, the last part of the question is why we talked about the total energy of the circuit. This is the total energy of the circuit. Now they're asking, what is the internal energy on the resistor? So as this charge is moving around, right, the resistor, well, this is an idealized drawing, right? The resistance is along the entire wire, but we're going to consolidate it into an object, call it resistor. So basically, as electrons are moving around, redistributing themselves, the wire heats up. The energy, the internal energy of the wire itself increases. So the wire heats up, and how much energy is on that resistor, basically, is what's asking. Well, we look at the total energy. Well, the total energy, so account for everything, it should be the energy on one capacitor, the energy on the bigger 3 capacitor, right? Plus the energy that's in the wire. So the key here is that we know the total energy, and then we're adding the pieces of energy that are in the circuit, the 2 capacitors and the resistor. So that accounts for all the energy of what we can talk about. So then we just add them together, subtract it to the other side, and we get this. So that is the internal energy on the resistor. Cool? Questions? No? Okay. Cool.